Tonight, we're going to explore one of the most uncomfortable truths in modern spaceflight. For more than 50 years, we've been told that the moon was just the beginning, that Mars was next, then the outer planets, then the stars. But what if that's not true? What if the moon wasn't the first step into deep space at all? What if it was the farthest humans were ever realistically going to go? The moon sits just 240,000 miles from Earth. Apollo reached it in only 3 days. By all appearances, it seemed like the start of a new era. Yet more than half a century later, no human has traveled farther. And the reason isn't a lack of ambition. It isn't politics. It isn't even technology. The deeper scientists and engineers look at the problem, the stranger it becomes. Because beyond the moon, almost everything starts working against you. Radiation, fuel, time, distance, human biology, life support, communication delays. Tiny failures that become deadly when Earth is no longer close enough to help. Each challenge looks difficult but manageable on its own. Put them together, and they create a barrier that may be far more serious than most people realize. By the end of tonight, you're going to understand why the moon may have been a very special exception, rather than the beginning of humanity's journey into deep space, why reaching Mars is far harder than most people imagine, and why some experts believe the greatest obstacle to exploring the solar system isn't engineering at all. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. It took Apollo just 3 days to reach the moon. That number has settled into the popular imagination as proof that space travel works, that the gap between Earth and moon is a problem humanity already solved. And in a narrow sense, that is true. The Apollo crews crossed roughly 240,000 miles of empty space, arrived, walked on another world, and came home. The mission worked, but let's think about what working actually required. The moon sits about 384,000 kilometers from Earth. That distance changes slightly as the moon moves through its orbit, but 384,000 kilometers is the number worth holding onto. In terms you can feel, if you could drive a car at highway speed without stopping, without sleeping, without the road ever ending, you would reach the moon in about 5.5 months. A commercial jet, flying continuously at cruising speed, would take roughly 22 days. The Apollo spacecraft covered the same distance in 3 days. That means the Apollo ship was moving at something close to 10 to 11 kilometers per second, roughly 36,000 to 40,000 kilometers per hour, around 25,000 miles per hour. Faster than anything you would encounter in ordinary life. Faster than any jet, any rifle bullet, any hurricane. And yet, in the vocabulary of space, that speed is almost leisurely. The universe is so large that even 25,000 miles per hour barely registers. This matters because the intuition most people carry from the Apollo success is built on that speed. They hear 10 kilometers per second and they think, fast. What the rest of this script will show is that 10 kilometers per second is not fast enough. Not for Mars. Not for the distances that come after the moon. But that comes later. For now, hold on to the moon. In light terms, the moon is about 1 light second away. 1 light second means that light, traveling at 186,000 miles per second, takes approximately 1 second to cross the Earth-Moon gap. Radio signals travel at the same speed as light. So when Mission Control in Houston sent a transmission to the Apollo astronauts on the lunar surface, that signal arrived about 1.3 seconds after it was sent. The reply came back another 1.3 seconds later. Round trip, roughly 2.5 seconds. Think about what 2.5 seconds means in practice. A normal conversation can absorb a 2.5 second delay. It is uncomfortable, like a bad international phone call where you hear your own voice echo back slightly after you speak. You pause a little longer before talking. You learn to wait, but the conversation still works. The information still flows. Mission Control could hear Neil Armstrong's voice, understand his words, respond with guidance, and receive confirmation. Not in real time exactly, but close enough that human judgment could still supervise the mission as it unfolded. That is the crucial word, supervise. The people on the ground could still watch, react, and intervene on a timescale that matched human attention. A problem that developed in 2 seconds could receive a response in 5 seconds. A navigation correction could be discussed agreed upon, and executed inside a minute. The moon was far enough that the delay existed, but close enough that the delay barely mattered. This is what made the moon a special case. Not just the distance, not just the speed. The combination of those two things with the signal lag produced something rare in space travel. A mission where Earth and the crew could still behave as though they were in the same room. Almost. The astronauts were independent, yes. They made decisions, but they were never truly cut off. They were never operating beyond reach. Houston could always see what they were seeing, almost as it happened. That feeling of connection is what the moon gave us, and it is exactly what makes going farther so different. Because the moment you move beyond the moon, that 2.5-second round trip begins to stretch. Not slowly, but immediately. Mars, at its closest approach to Earth, sits roughly 140 times farther away than the moon. The signal delay does not stay at 2.5 seconds. It does not nudge up to 5 or 10 seconds. It jumps to something between 6 and 45 minutes, depending on where Mars and Earth are in their orbits. That is a round-trip communication time measured not in seconds, but in hours. The conversation stops working. Supervision stops working. Everything built on the assumption of near-instant contact stops working. But that is where the script is going. For now, the moon is still the frame of reference. 3 days, 10 kilometers per second, 1 light second, a 2.5-second delay that felt like nothing, a 1960s mission that came home safe. The question the rest of tonight is really asking is this: why did that success teach us almost nothing about what comes next? Why is the moon not a first step, but a singular event, shaped by conditions that do not repeat the moment you travel farther? The answer begins with one number, a number that sounds familiar, even modest, until you ask what it means to change it. That number is fuel. Start there, and everything else that follows tonight begins to make sense. Not the engineering, not the life support, not the communication problem already described, the fuel, because every constraint on human spaceflight, from the moon outward, bends back to one physical fact about how rockets work. The fact has a name, delta V. It is pronounced exactly as it looks, the Greek letter delta meaning change, and V standing for velocity. What it describes is the total change in speed a spacecraft needs to complete a mission. Think of it as a budget, a speed budget. Every burn of the engine costs something from that budget. Accelerating out of Earth's orbit costs some of it. Braking into lunar orbit costs some of it. Descending to the surface costs some. Launching back off costs more. Returning to Earth and slowing down for re-entry costs the rest. Every maneuver, every correction, every adjustment draws from the same account. When the account is empty, you stop moving the way you intended. For a full round trip to the moon and back, from Earth's surface through low Earth orbit, out to the moon, down to the surface, back up, and home, that budget adds up to roughly 10 to 11 kilometers per second of total delta V. That is the number, 10 to 11 kilometers per second. The same speed the Apollo missions flew, which was introduced earlier tonight. But now we are using it differently. We are asking not how fast the spacecraft moved, but how much total speed change the engines had to produce across the entire journey. That number explains something that has always struck people as slightly strange about rockets. Look at any photograph of a launch vehicle sitting on the pad. The capsule, the part that carries the crew, sits at the very top. It is small. Sometimes it looks almost comically small relative to the enormous machine beneath it. The rest of the structure, nearly all of it, is propellant. Fuel and oxidizer and the tanks to hold them, and the engines to burn them. Not payload, not people. Fuel. This is not a design inefficiency. It is a mathematical requirement. And that mathematics is where the first real surprise of tonight lives. Here is what most people assume when they first hear about the rocket equation. More speed means more fuel. Double the desired speed change. Use roughly double the fuel. It seems reasonable. It is wrong. Not a small error. Not an approximation that gets close. Completely wrong in structure. Fuel does not scale linearly with desired speed. It scales exponentially. And the difference between linear and exponential is the difference between manageable and crushing. Think about compound interest for a moment. A savings account growing at a fixed annual rate does not grow by the same dollar amount each year. It grows by a fixed percentage of whatever the balance already is. So the bigger it gets, the faster it grows, and the faster it grows, the bigger it gets. The growth feeds on itself. Now, run that same structure in reverse and you have the rocket equation. Every extra unit of speed you want the rocket to reach requires not just more fuel, but more fuel to push the fuel you already have, plus more structure to hold all of that fuel, plus more fuel to push that structure. The cascade keeps building on itself. Here is what that looks like in practice. Imagine you have a rocket designed to deliver a certain payload to a certain speed. You decide you want a little more speed, not twice as much, just a meaningful fraction more. The fuel mass does not increase by that same fraction. It increases by a much larger factor, because the new fuel also has to be accelerated along with everything else, which means you need more fuel still to push it, which means heavier tanks, which means more fuel to push the heavier tanks, which means the vehicle has grown far beyond what the original speed increase seemed to warrant. Each step in the cascade is real. Each step demands its own answer. The answer is always more mass, and more mass always demands more fuel. This is the rocket equation. It was described precisely in 1903 by a Russian schoolteacher named Konstantin Tsiolkovsky. The equation he wrote down tells you exactly how much propellant you need to achieve a given delta V, given the exhaust velocity of your engine. The relationship is exponential. That has not changed. No engineering refinement has changed the underlying shape of the curve. So the moon round trip, requiring 10 to 11 kilometers per second, sits at the edge of what chemical rockets can realistically deliver. By the time you account for the cascade, a Saturn V launched roughly 3,000 tons of vehicle to put about 45 tons into low Earth orbit, and ultimately to carry about 30 tons to the moon. The mass ratio is not comfortable. It is not generous. It is the result of fighting the rocket equation as hard as 1960s engineering could manage, and barely winning. But here is where it gets strange. Going to Mars is not just a bigger moon mission. It is not the next step on the same curve. A full Mars mission, including capture into Mars orbit, descent to the surface, launch back off the Martian surface, and the return to Earth, requires somewhere between 15 and 20 kilometers per second of total delta V. Not 10 to 11, 15 to 20. That gap looks narrow on paper. 4 to 9 kilometers per second, separating a mission that worked from a mission that has not yet happened. But because the fuel-mass relationship is exponential, not linear, that gap in delta phi corresponds to a disproportionate increase in everything else. The vehicles required do not grow by the same factor as the delta V. They grow by much more. The phrase used by engineers and mission planners when describing what this does to a vehicle design is crushing. The spacecraft becomes almost entirely propellant, with a small pressurized section for the crew tucked somewhere inside the mass. The ratio of fuel to everything else gets worse with every extra kilometer per second of delta V, and the Mars mission demands quite a lot of extra kilometers per second. The moon sits at a very specific place in this relationship. It is the last destination where the rocket equation, while brutal, is still survivable. You can build a vehicle that gets there and back. It takes an enormous machine, and it leaves almost no margin, but the mathematics close. They just barely close. Beyond the moon, they stop closing in the same way. The curve does not level off. It does not slow down. It steepens. What was very hard becomes something closer to structurally impossible without a different approach entirely. The moon was not a first step toward the planets. It was the last step before the rocket equation really turns against you. The Apollo program sat right at the edge, and the engineers who built it knew how close to that edge they were. And that edge is only the beginning of why Mars stays so far out of reach. The fuel problem is the foundation. The other constraints stack on top of it. The first of them has a history. Between 1969 and 1972, 6 Apollo missions landed humans on the moon. 6. In the more than 50 years since, that number has not moved. 6 landings represent the entire human record of leaving Earth. Not the record so far, pending a 7th. The record, full stop, for every human being who has ever lived. Think about what that took. The Apollo program cost roughly $25 billion in 1960s era money. Adjusted for inflation, the estimates run between $150 and $200 billion or more in today's terms. Spread across 6 landings, that is somewhere between $25 and $33 billion per trip at minimum. Each mission required a Saturn V rocket, the height of a 36-story building, built from scratch, used once, and discarded into the ocean. The lunar module flew twice, briefly, and was abandoned on the moon or burned in re-entry. The command module splashed down and retired. Nothing was reused. Nothing fed into the next mission as a foundation. Apollo was not a transport system. It was a custom machine, assembled from the ground up for each flight. The industrial surge required to build it was enormous. The political will required to sustain it was exceptional. And the moment the political pressure eased, the program ended. Not wound down slowly, ended. 3 planned moon landings were cancelled outright. That is not the behavior of a first step in a sequence. That is the behavior of a maximum effort that reached its natural limit. But the picture did not hold. Even that maximum effort, even those 6 barely affordable missions, carried a hidden advantage that had nothing to do with engineering. The astronauts who flew to the moon were not fully outside Earth's protection. Not for most of the journey. Earth is surrounded by a magnetic field, the magnetosphere. It acts as an invisible shield, deflecting high-energy charged particles streaming from the sun and from deep space. Inside that field sits the Van Allen radiation belts, regions where charged particles have been trapped and concentrated by the magnetic geometry. The radiation levels inside the inner belt are genuinely dangerous. Exposure for long enough causes tissue damage, raises cancer risk, and can impair the central nervous system. Apollo crews flew through those belts, but the trajectories were carefully chosen to cross the thinnest regions, where the particle density was lowest, and the crossing was made as quickly as possible. For most of the journey between Earth and Moon, the astronauts were still partially inside the outer edges of Earth's magnetic influence. The shield had not fully disappeared. It had simply thinned. Mission length did the rest. A round trip to the Moon lasted roughly 1 week to just under 2 weeks. At that duration, the total radiation dose stayed within limits that were considered acceptable at the time, though not comfortable. The brevity of the mission was itself a form of protection. Here is what most people assume when they think about Apollo radiation safety. They assume the spacecraft shielding handled the problem. The metal hull, the thick walls, the engineering of the vehicle. That assumption is wrong. The shielding was minimal. The vehicle walls were not designed to stop radiation in any serious way. What protected the Apollo crews was geometry and timing. Earth's magnetic field still partially reaching them. The short duration keeping the cumulative dose below a critical threshold. Neither of those was primarily a technological achievement. Both of them were a gift from the specific conditions of the Moon mission itself. On a mission to the Moon, radiation is a short storm you sprint through. You enter the thin part of the belts, cross quickly, spend a few days in open space that is still relatively nearby, and come home before the dose accumulates into something serious. On a mission to Mars, that analogy collapses entirely. The magnetic field falls away within a few 100,000 kilometers of Earth. Past that, there is nothing. No shield, no thinning belts to thread. The full radiation environment of interplanetary space, unattenuated, for 6 months in each direction. On a Mars mission, radiation is not a storm you sprint through. It is the climate your crew lives in for the entire journey. And this matters not as an isolated problem, but as another constraint that feeds back into the others. More shielding means more mass. More mass means more delta V. More delta V means more fuel. More fuel means more structure to hold it. More structure means still more mass. The cascade is the same one the rocket equation already started. Adding shielding does not solve the radiation problem in isolation. It taxes every other system simultaneously. The Moon avoided that cascade, not by solving it, by being close enough, and brief enough, and positioned inside a fading magnetic field that the problem never fully materialized, which leads to the deeper mistake, the one that runs underneath all of this. When people hear that humans went to the Moon in 1969 and ask why we have not reached Mars yet, they are usually thinking in a straight line. The Moon is 400,000 kilometers away. Mars is roughly 400 million kilometers at favorable alignment. That is about 1,000 times farther. So the instinct is to imagine a Mars mission as a Moon mission scaled up by roughly that factor. More fuel, more food, more time, same structure, larger version. Space does not scale like a road. On a road, driving 1,000 times farther means roughly 1,000 times more of everything. Distance is the only variable. In space, every extra kilometer of distance ties to more velocity, more energy, more fuel, more shielding, more life support, more redundancy, and all of those variables couple back into each other. The relationships are not linear, they compound. Adding shielding makes the fuel problem harder. Adding life support for a longer mission makes the mass problem harder. Making the mass problem harder makes the shielding problem harder again. Every constraint tightens every other constraint. The moon was a special case where distance, travel time, radiation, and gravitational geometry all landed inside a narrow window. A window where mid-20th century technology, at extraordinary cost and with a hidden magnetic field advantage, could just barely succeed. That particular combination does not extend outward. Past the moon, every one of those variables moves in the wrong direction at once. The window that made Apollo possible closes, and what opens in its place is a different category of problem entirely, not a harder version of the same challenge, a different kind of challenge, where the old tools stop working in the same way and new ones have not yet been built. That shift, from one regime to another, is what the rest of this story is about. Let's stay with that idea for a moment. The tools stop working in the same way. What does that mean in practice? It means the first tool we need to examine is the most basic one: gravity itself. Gravity does not feel like a prison because we were born inside it. It feels like the floor beneath your feet, the weight of your arms, the reason a glass falls when you drop it. But for anything trying to leave Earth permanently, gravity is the defining constraint. Every engine ever built, every staging maneuver ever designed, every rocket equation ever written down is an attempt to cheat that one fact. The price of leaving Earth is specific. To break free entirely, not just reach low orbit but escape Earth's gravitational pull, you need to reach a speed of approximately 11.2 kilometers per second. That translates to roughly 40,000 kilometers per hour. You may remember from earlier that Apollo crews flew at around that same figure. Reaching escape velocity is not a bonus achievement. It is the entry requirement. Here is a way to feel that number. A rifle bullet travels at about 1.2 kilometers per second. That is already fast enough that you cannot follow it with your eyes. Escape velocity is roughly 30 times that. Not twice as fast as a bullet, not 5 times, 30. That is the floor. And reaching that floor is not a smooth, gradual process. A rocket lifting off from the launch pad is not drifting upward. It is slamming against gravity and atmospheric drag simultaneously, burning tons of propellant every second, shaking hard enough that structural engineers design for frequencies that would destroy the vehicle if they resonated at the wrong moment. Ascent rides a narrow line between controlled flight and explosion. The crew inside experiences 3 to 4 times their own body weight, pressing them into their seats. Not a gentle climb. A sustained physical assault that lasts for minutes. To survive it while actually reaching 11.2 kilometers per second, rocket stage. They drop empty tanks, ignite fresh engines, and discard spent hardware so the remaining vehicle keeps getting lighter as it gets faster. Each stage is a separate machine, used once and discarded. The payload at the top, the part you actually wanted to move, is a small fraction of what left the ground. But escape velocity is only the beginning of the accounting. A mission needs more than bare escape. It needs the velocity to reach low Earth orbit first, then to break out of orbit, then to navigate toward a destination, then to slow down at arrival, then to launch from the surface there, then to return. Each maneuver draws from the total speed budget. We covered this earlier as delta V, the cumulative velocity a spacecraft must produce across its whole mission. The cruel arithmetic is what happens when you add up the full mission and run it backward through the rocket equation. The rocket equation does not work the way most people expect. The expectation is reasonable. More mission means more fuel in roughly the same proportion. Double the distance, roughly double the fuel. This was already shown to be wrong in how it applies to Mars, but it is worth applying that same lens directly to the launch itself. Here is where the engineering becomes uncomfortable. For a crewed mission to deep space and back, when engineers close all the numbers, between 90 and 95% of what sits on the launch pad is propellant. Not the spacecraft, not the life support systems, not the crew cabin. Propellant, the vehicle that looks enormous on the pad, the machine that shakes the ground when it ignites, is almost entirely a container for fuel. The actual mission, the hardware the crew lives in, is a small bubble attached to the top of an enormous flying fuel tank. Most people who hear this assume the fix is obvious. Use a better engine. And there are better engines. Several kinds. Chemical liquid engines, which have powered every human mission so far, produce a specific impulse of roughly 300 to 450 seconds. Specific impulse is a measure of how efficiently an engine uses its propellant. Think of it as fuel economy, how much push you get per unit of fuel burned. 300 to 450 seconds is a rough measure of how long 1 unit of propellant can sustain 1 unit of thrust. Nuclear thermal engines would do better. By heating hydrogen propellant with a nuclear reactor instead of burning it chemically, you could roughly double the specific impulse, maybe more in some designs. That is a real improvement. Electric propulsion, ion engines, and Hall thrusters goes much further. Specific impulses in the thousands of seconds. The numbers suggest these engines should solve everything, but the reality is different. More efficient engines do not automatically mean faster or easier missions. Efficiency measures how well an engine uses its propellant. It does not measure how much force the engine actually produces, and that distinction matters enormously. Chemical engines are inefficient by comparison, but they generate enormous thrust. Thrust is what fights gravity. Thrust is what pushes a vehicle upward against the force trying to hold it down. You cannot lift a crewed spacecraft off the ground or produce the large, rapid velocity changes a crewed mission requires with an engine that produces tiny thrust over months or years. Electric engines produce very small thrust, not modest thrust, tiny, the kind of force you might feel from a gentle breath on your hand. They work for robotic probes that have months or years to slowly accelerate through the vacuum of deep space. They are essentially useless for lifting anything off a planetary surface, or for the large, fast velocity changes that make a human mission survivable in terms of total transit time. So the trade looks like this: chemical engines, high thrust, moderate efficiency, near the ceiling of what chemistry can offer. Nuclear thermal, higher efficiency, better performance, but complex to build and operate, with radiation challenges that add mass and cost to manage. Electric, extraordinary efficiency, negligible thrust, no use for the heavy lifting a crewed mission requires. Each type of engine fixes one half of the problem. None of them fixes both halves at once. And the ceiling on chemistry is not a temporary limitation waiting for a breakthrough. It is a physical one. The energy you get from burning propellant comes from rearranging atoms into different molecules. Hydrogen and oxygen combining into water, carbon compounds releasing heat. The amount of energy stored in those chemical bonds is fixed by atomic physics. You cannot get 10 times more energy from the same kind of reaction by engineering more cleverly. The ceiling is built into the nature of matter itself. Nuclear helps, but nuclear is not unlimited either. It brings radiation shielding requirements, which add mass, which increases the delta V demand, which increases propellant, which increases mass again. The cascade does not disappear. It shifts. So the two obvious solutions, build a bigger rocket and use a better engine, each dissolve on contact with the full set of constraints. A bigger rocket means exponentially more propellant to push more propellant, and the returns diminish toward near vertical on the curve. A better engine means gaining efficiency at the cost of thrust, or gaining thrust at the cost of efficiency, and neither combination closes a full crewed deep space mission cleanly. Gravity sets the price. The rocket equation multiplies it. And the ceiling on energy density means you cannot simply buy your way out by burning more of the same thing. The propulsion problem and the mass problem are not separate problems. They are the same problem described from two directions, and solving one end without the other just moves the wall. That constraint does not stand alone either. It connects directly to the next one, and that connection is where the accounting gets harder still. So follow the ship, watch it burn through its last stage, shed the empty tanks, and climb above the atmosphere. At this point, Earth still has it. Earth's gravity reaches outward in every direction, but that reach is not infinite. There is a boundary, roughly 1.5 million kilometers from Earth, roughly a million miles, where the sun's gravity begins to outpull Earth's for any object trying to stay in orbit. Inside that boundary, Earth is the dominant force. Your orbit makes sense in terms of Earth. Beyond it, the sun takes over, and Earth becomes, in the language of mission planners, a local detail. That boundary has a name. It is called the Hill Sphere, after the astronomer George Hill, who calculated the geometry of gravitational dominance between competing bodies. Think of it as a domain boundary, the edge of the territory where one set of rules gives way to another. Inside it, you're planning a trip around a planet. Outside it, you are planning a trip around the sun, and the planet you just left is simply one point on that orbit. The moon sits comfortably inside Earth's Hill sphere. That proximity is part of why Apollo worked, not just in terms of fuel and communication, but in terms of geometry. Earth's gravity was still the context. The trajectory was still local. The moment you push past that boundary toward Mars, you have left the local context behind. You are now navigating a heliocentric orbit, a path shaped by the sun's gravity, and the rules governing where you go and when you can leave are no longer Earth's rules. They are the sun's. And that changes everything about timing. To reach Mars, you cannot simply point at it and burn. Mars is not waiting at a fixed location. It moves. Earth moves. The angle between them changes continuously, and the only moment when a direct, fuel-efficient transfer is available is when the two planets are correctly aligned. That alignment follows a rhythm. It comes around roughly every 26 months. That is your window. A trajectory called a Hohmann transfer, a carefully calculated arc that follows the sun's curvature between two orbital paths, requires you to launch during that window, not close to it. During it, miss the window and your options collapse quickly. You can attempt a different path. Some exist, but they are dramatically less efficient. They demand far more delta V, which cascades back into the mass problem with full force. You are not paying a small premium for flexibility. You are reopening the entire exponential accounting we walked through before, except now from a larger starting point. The numbers do not close, so the mission is locked. The crew does not leave when the vehicle is ready. They leave when the geometry is ready, and if something slips in the schedule, they wait. Not days, not weeks, 26 months. Something else is happening. Even if you hit the window perfectly, even if the alignment is ideal and the Hohmann transfer is calculated correctly, you still have to carry everything you will need for the entire journey on the day you leave Earth. That is the mass penalty cascade, and in the context of a multi-year deep space mission, its scale is something most people have not fully absorbed. Consider food. 1 kilogram of supplies per person per day is a reasonable estimate for a stripped-down mission. A crew of 6 on a 2-year round trip to Mars is not bringing 12 kilograms of food. They are bringing more than 4,000. That is before redundancy. That is before the possibility of delays. Just the arithmetic of keeping 6 people alive at the lower bound produces tons of mass that must be accelerated out of Earth's gravity well and pushed onto an interplanetary trajectory. Then add shielding. The radiation environment on an interplanetary transit, which we have already traced, requires shielding mass that runs into many additional tons depending on the approach chosen. Add spare parts for systems that will run continuously for years, with no maintenance from Earth. Add tools. Add science instruments, because a mission that spends billions in development and decades in planning is not going to Mars to look out the window. Add a lander, because the crew has to get from Martian orbit to the Martian surface. Add a rover if the science requires surface mobility. Add contingency reserves for each of these categories, because a failed component on a 2-year mission with no resupply option is not an inconvenience. It is a survival event. Each of those additions is not just weight. Each kilogram added to the payload has to be lifted from Earth's surface, burned through Earth's atmosphere, accelerated to orbital velocity, pushed past the Hill sphere boundary, and then placed on a Hohmann transfer arc. That last step alone costs significant delta V, which means more fuel, which means more structure to hold the fuel, which means more mass to push, which means more fuel again. The cascade we traced in the rocket equation does not wait politely while you add items to the list. It compounds every addition immediately. For a moon mission, this cascade was painful but survivable. Apollo carried what it needed and nothing more, and the short duration and modest delta phi requirement kept the mass within the range that the Saturn V, built at enormous cost and discarded after a single use, could manage. The numbers closed, barely, at the outer edge of what was technically possible. For a multi-year Mars mission, the same cascade does not compress. It blows through the budget. Every addition on the list triggers a reaction that propagates through the entire vehicle design, demanding larger tanks, stronger structure, more propellant, more launch capacity. Engineers call this point the moment when the mass required to carry the mass overwhelms any achievable launch system, the point where the design no longer closes. The numbers do not balance. The vehicle required to carry the vehicle exceeds what any rocket can lift. Gravity does not stop you with a wall. There is no hard barrier that prevents a ship from leaving. What gravity does is something more patient. It makes every decision expensive. It makes every kilogram of good intentions into a multiplying liability. It makes the window narrow and the timing strict, and the mass cascade relentless. And it means that beyond the moon, you are not simply farther from home. You are playing a different game, one where the sun is the jailer, the calendar is locked by orbital mechanics, and the mass you carry is never just itself. It is always also the price of carrying it. That was the geometry and the weight. But mass is not the only thing you have to carry for 2 years. The crew has to survive the journey, and survival in deep space raises a set of problems that mass alone cannot solve. Let's say you solved all of it. Let's say the rocket equation closed. Let's say the launch window aligned, the fuel loaded, the delta V accounted for, and the ship left Earth's gravitational domain right on schedule. What greets you in that empty space between the planets? Not silence, not safety. Something else entirely. There is a background to deep space that does not care about orbital mechanics or fuel budgets. It does not respond to clever engineering or lighter materials. It attacks the crew whether the ship is moving fast or slow, whether the trajectory is optimal or compromised. It attacks the electronics too, and the hull, and the computers running every system that keeps the crew alive. It has been doing this since the solar system formed, and it will be doing it long after any mission ends. Radiation is not a hazard you pass through on the way to deep space. It is the climate of deep space. To understand how different that is, start with a baseline. Astronauts aboard the International Space Station absorb roughly 80 to 160 millisieverts of radiation during a standard 6-month mission. That is a meaningful dose. Doctors use millisieverts to measure medical scans, and a single CT scan delivers roughly 10 to 20 millisieverts. An ISS astronaut accumulates the equivalent of several CT scans, stretched across half a year. Not instantly dangerous, but measurable, and it raises long-term cancer risk in a way that occupational health guidelines take seriously. The ISS sits at roughly 400 kilometers above Earth's surface, about 250 miles up. That sounds high. It is not high enough to escape Earth's magnetic field. The magnetosphere, the invisible shell of charged particles and field lines surrounding our planet, still extends far above the station's orbit. The ISS is still partially inside Earth's protection. The radiation number, already non-trivial, reflects a partially shielded environment. A Mars mission removes that shield almost immediately after departure. Within a few 100,000 kilometers of Earth, the magnetic field fades to background. Beyond that, you're exposed to interplanetary space on its own terms. The Curiosity rover carried a radiation detector during its cruise to Mars, not as an afterthought, but as a deliberate measurement. Scientists wanted real data, not models. What that detector recorded across a 6-month cruise phase matched what models had predicted, and the number was not reassuring. A round-trip Mars mission, including transit both ways and time on the surface, would expose an astronaut to somewhere between 0.6 and 1.0 sievert of total radiation dose. 1 sievert equals 1,000 millisieverts. Think about that conversion for a moment. A 6-month ISS mission delivers up to 160 millisieverts. A Mars round trip delivers 600 to 1,000. That is roughly 10 times the already elevated dose an ISS astronaut receives, delivered across a mission lasting 2 years or more. Lifetime cancer risk for each crew member rises by tens of %. This is not an estimate based on guesswork. These are real measurements from a real instrument in real deep space. But here is where it gets strange. Your first instinct, if you are thinking like an engineer, is to add shielding. Thicker walls, heavier hull, more material between the crew and the particles hitting the ship. That instinct works for most forms of radiation. It does not work cleanly for galactic cosmic rays. Galactic cosmic rays are not solar radiation. They are not products of the sun. They are high-energy particles, mostly protons and atomic nuclei, accelerated to near-light speeds by supernovae and other violent events scattered across the galaxy. They arrive from all directions, continuously. They pass through ordinary shielding the way a rifle round passes through paper. When they hit DNA directly, they can break strands, cause mutations, damage the molecular machinery inside cells. The body repairs some of this constantly, but galactic cosmic ray exposure accumulates faster than repair mechanisms can compensate. Over months and years, the damage builds. Now here is the counterintuitive part. If you try to stop galactic cosmic rays with a thick layer of lead or any other dense metal, you can make the problem worse. When a high-energy particle smashes into a heavy nucleus inside the shielding, the collision generates secondary particles, fragments, showers. The incoming ray splits into a spray of lighter particles that scatter through the ship. Behind a thick lead wall, the crew might absorb more radiation than they would behind a thin one. The materials that actually help are hydrogen-rich, water, polyethylene, a plastic whose molecular structure is dense with hydrogen atoms. Hydrogen is light enough that collisions slow the incoming particles without generating the same cascade of secondaries. The physics favors the simple molecule over the heavy metal. But to meaningfully reduce the dose, the crew cabin needs roughly 20 to 30 centimeters of water or plastic on all sides, 8 to 12 inches, all the way around. For a cabin housing 6 people across a 2-year journey, that shielding has the mass of a small swimming pool, several tons, just to wrap the living space in a layer of hydrogen-rich material. And it still does not stop galactic cosmic rays entirely. It reduces them. The dose behind adequate shielding is lower than without it, but not zero, not safe, and not a solved problem. The acute threat is different. Solar flares, sudden eruptions from the sun's surface, can release enormous bursts of charged particles in hours. The chronic background of galactic cosmic rays is the slow accumulation. A solar flare is the acute event that can kill quickly. In 1972, between the Apollo 16 and Apollo 17 missions, the Sun released one of the most powerful solar flares in the modern observational record. Calculations performed after the fact showed that if astronauts had been on the lunar surface during that event, protected only by Apollo-grade spacesuits and the thin shielding of the lunar module, they could have received a lethal radiation dose in a matter of hours. Apollo missed the 1972 flare by timing alone. There were no astronauts in deep space when it hit. The program happened to be between missions. That is not a safety system. That is luck. A 2-year Mars mission cannot be structured around luck. The crew will be in deep space for enough time that one or more significant solar storms are statistically probable. The mission must assume a major flare will occur mid-journey, and it must have an answer ready. That answer is a dedicated storm shelter, a smaller volume with substantially thicker shielding than the main cabin, where the crew retreats and waits for hours or days while the particle flux passes. It needs radiation monitors. It needs warning systems. It adds more mass to a ship already burdened by everything discussed before this moment. Radiation does not limit its damage to the people aboard. It attacks the ship as well. High-energy particles flip individual bits inside computer memory. A single bit flip in the wrong register can corrupt data, cause a miscalculation, crash a process that controls life support or navigation. Over months and years, the cumulative effect degrades solar panels, weakening their ability to generate power. It damages sensors. It slowly compromises the physical properties of structural materials. Voyager 1 and Voyager 2 have survived for decades in deep space, partly because they are allowed to fail occasionally, to operate with degraded systems, to lose sensors and keep transmitting. A crewed ship cannot operate that way. Every critical system needs radiation-hardened electronics designed to keep functioning after repeated particle strikes. Multiple redundant copies of vital computers need to be shielded separately, so a single hit does not cascade into a mission-ending failure. All of that is additional mass, more hardware, more shielding around the electronics, and this is where the constraint closes into a loop. More shielding to protect the crew adds mass. More mass requires more fuel. More fuel means a heavier ship that accelerates more slowly. A slower trajectory takes longer. A longer mission means more time in deep space behind the shielding. More time in deep space means more cumulative radiation exposure, even behind that shielding, because galactic cosmic rays accumulate continuously across every day of transit. The two ends of the dial are both losing positions. A lightly shielded ship exposes the crew to a dangerous dose on a fast mission. A heavily shielded ship turns a manageable mass problem into a potentially unclosable one, and still delivers a meaningful radiation dose on the longer mission that the heavier ship requires. There is no version of more armor that fully solves the problem. The physics of shielding and the physics of mass push against each other, and neither yields. We do not yet know what the combined effect of years of galactic cosmic ray exposure alongside months of microgravity actually does to a human body. Nobody has spent 2 years in deep space. The long-term interaction of those two stresses, radiation damage accumulating in DNA while gravity-dependent systems in the body are simultaneously degrading, has never been measured in a living crew. The data does not exist because no mission of that type has ever flown. That gap alone is enough to pause the planning, and it is only one part of what survival in deep space requires. Let's stay with the longer trip half of that loop for a moment, because the word longer is doing a lot of work there, and it deserves to be unpacked. Distance in space is not really a question about how far something is. It is a question about how long you are committed. And once you understand that, the Mars problem changes shape entirely. Mars is not a fixed target. The distance between Earth and Mars varies enormously depending on where both planets sit in their orbits around the Sun. At close opposition, when the two planets are on the same side of the Sun and near each other, the gap narrows to roughly 55 million kilometers, about 34 million miles. At maximum separation, when they sit on opposite sides of the Sun, the distance stretches past 400 million kilometers, more than 250 million miles. The average works out to around 225 million kilometers, about 140 million miles. That variation matters because it is not just a geographical fact. It sets the rhythm of every possible departure. With chemical rockets, the transit from Earth to Mars takes roughly 6 to 9 months one way, depending on the launch window. 6 months is close to the length of a human pregnancy. In a small ship, with no backup hospital, with no possibility of turning around. The Moon, by contrast, spoiled us. The geometry was forgiving. The distance was roughly constant. Missions could launch with some flexibility in timing. And if something went badly wrong, the crew was never more than a few days from home. Mars strips all of that away at once. Here is the structure that makes Mars so rigid. To reach Mars with chemical rockets, you do not simply point at it and fire. You follow what is called a Hohmann transfer, an arc that curves outward from Earth's orbit, and intersects Mars's orbit at the far end. Think of it less like driving and more like throwing a stone across a very large room, angling your throw not at where the target is now, but at the empty spot where the target will be when the stone arrives. The geometry only works when Earth and Mars are aligned in a specific way. That alignment comes around roughly every 26 months. Miss the window, and your options are not good. You can wait 26 months for the next one. Or you can force a trajectory outside the optimal alignment, which demands dramatically more fuel, which reopens the entire mass cascade that earlier sections described. There is no version where leave whenever you want is a real choice. And once you're on that arc, you are not steering a car. You burn hard at departure to set your trajectory, make small correction burns along the way, and then coast. You are following orbital mechanics, curving around the Sun like a stone in flight. The energy cost of stopping mid-trip and reversing course is not merely high, it is catastrophic. You do not have that fuel. It was not part of the plan because it was never going to be part of the plan. You are committed for months from the moment the main engines cut off. The natural impulse at this point is to ask why we cannot simply go faster. Shorten the trip from 6 months to 6 weeks. Less exposure to radiation, less time for something to break, less stress on the crew. The instinct is right. The physics is unkind. For a real speed up, you would want a ship that accelerates continuously, building speed through the first half of the trip, and then flipping and decelerating through the second half. If you could accelerate at 1 gravity, the same 9.8 meters per second squared that you feel standing on the floor of a room right now, you would cover huge distances in surprisingly short times, and the crew would feel like they were standing on solid ground the entire journey. That matters for reasons beyond travel time, but continuous acceleration at 1 gravity requires engines nowhere near what chemical rockets can provide. It would require advanced nuclear propulsion at minimum, and likely something beyond that. What we have now is a different profile entirely. Hard blast off, hit high speed, then coast. You do not have a throttle you can keep pressed. Chemical engines deliver enormous thrust for a few minutes, burn through their propellant, and go quiet. The rest of the trip is free fall. That profile is not a design choice. It is the ceiling of what current technology allows. And here is where the time problem bites hardest. A 6 to 9 month transit each direction, plus time on the surface, means a full Mars mission runs somewhere around 3 years. A crew of 4 on a 3-year mission, even with recycling systems running, requires several kilograms of water, food, and oxygen per person per day by NASA planning standards. Stack that across 4 people for 3 years, and you are looking at tens of tons of consumables before you account for packaging, pressurized tanks, and safety margins. That is not a rough number. It is a careful floor, and the floor is already very high. The alternative is closed-loop life support, systems that recycle water, process waste, and scrub carbon dioxide continuously without resupply. Less mass to carry, but more complexity. More pumps, more filters, more electronics, more chemical processes, all of which must operate flawlessly for years with no technician available and no replacement parts arriving from Earth. More time in operation means more chances for something to fail in a way that cannot be fixed. Either path means more time equals more risk. Store more supplies and the mass problem compounds. Rely on closed-loop systems and the failure mode problem compounds. There is no version of the calendar that makes this gentler. But the deepest expression of what time does to a Mars mission is not in consumables or recycling. It is in what happens when something goes seriously wrong. Apollo 13 is worth understanding carefully here. On April 13, 1970, an oxygen tank in the service module exploded roughly 56 hours after launch, crippling the spacecraft's power and life support systems. The crew faced a genuine threat of death. What saved them was not clever engineering alone. It was the moon's proximity. The mission could loop around the moon and use the free return trajectory to swing back toward Earth. The total time from the explosion to splashdown was just under 4 days. Every calculation, every improvised fix, every decision had a tight deadline, but also a fixed destination that was only days away. A Mars crew in a similar situation does not have that option. Not a slower version of it, not a harder version of it. The option does not exist. On a trajectory to Mars, the minimum energy path locks you in for months. The fuel planned for the mission is budgeted for the burns that mission requires, not for an unplanned reverse and sprint toward home. No rescue ship can launch on short notice and intercept you. You cannot stop and hold position while waiting for help. The distances involved, and the orbital mechanics that govern them, make a rescue mission physically impossible on any timeline that would matter. If life support begins to fail midway through the trip, only the systems already on your ship can save the crew. If a crew member suffers a serious medical emergency, there is no hospital, no surgeon, no supply chain, no possibility of evacuation. What is on the ship is what you have. Everything else is unreachable. Beyond the moon, engineers who have studied this problem use a phrase that is precise and sobering. Any major failure is almost automatically fatal. Not probably fatal, not likely fatal, almost automatically. The word automatically is doing real work there. It means the distance and the physics combine to remove the corrective options that saved Apollo 13. And that rescue in the deep solar system is not a difficult thing to arrange. It is a thing that cannot be arranged at all. Time, which sits on a mission plan as a neutral measurement, becomes a trap. The longer the mission lasts, the more opportunities exist for the kind of failure that cannot be recovered from. The distance does not just make the journey longer. It removes every mechanism that shorter distances allowed. That is the geometry of commitment, and it does not stand alone. What that commitment costs begins inside the hull. The human body did not evolve for space. It evolved for one very specific environment. Earth at one gravity, with air pressure, a day-night cycle, and a consistent up-down reference that never changes. Take that environment away for more than a few weeks, and the body does not simply wait for its return. It begins to reorganize itself around the conditions it finds. Bone is living tissue. It responds to the forces placed on it. Under one gravity, Your skeleton carries your weight every moment you are upright. The bones of your hips and spine and legs are constantly under load. That load is the signal the body uses to maintain density. Remove the signal, and the bones begin to shed mass. On the International Space Station, without aggressive countermeasures, crews lose roughly 1 to 2% of their bone mass per month. Not 1 to 2% over the whole mission, per month. Measured loss, concentrated in the hips and spine, the same regions that bear the most weight on Earth. Muscles follow the same logic. The legs and lower back exist largely to fight gravity. Without gravity, they are not needed in the same way. They atrophy. The response to this is exercise. On the ISS, crews spend roughly 2 hours a day on treadmills with harnesses that pull them toward the running surface, on resistance machines, on cycling equipment, 2 hours a day, every day, just to slow the deterioration, not stop it, slow it. After a typical 6-month ISS stay, crew members come home weaker than they left. They need rehabilitation just to walk normally on Earth. Now extend that to a 3-year deep space mission. 6 months out, time at the destination, 6 months back. The same processes continue through all of it. The skeleton is not merely deconditioned, it is being gradually dismantled and rebuilt for microgravity. Not weakened the way you might be weakened by a long illness, rebuilt. Structurally reorganized for an environment that has no flaw, but bone and muscle are only the beginning. Gravity normally pulls blood and fluid toward the legs. In microgravity, those fluids redistribute upward, toward the chest and head. Astronauts describe the sensation in a phrase that is clinical and vivid at the same time. Puffy face, chicken legs. The face swells with excess fluid. The legs thin out from its absence. That is not a cosmetic problem. Increased fluid pressure inside the skull and around the eyes causes measurable changes over long missions. The medical name is Spaceflight Associated Neuroocular Syndrome, SANS. Over the course of a long mission, vision changes. Some crew members become more far-sighted. Eyeball shape can shift slightly. The optic nerve can appear swollen on examination. MRI scans have shown that the brain itself moves inside the skull, and some brain regions appear to change in volume. The nervous system has no consistent up-down reference for months. The inner ear, the eyes, the balance sensors, the blood vessels, all of them send signals that do not match any pattern the human body evolved to process. It adapts, but adaptation to the conditions of microgravity is not the same as being undamaged by them. The two are not equivalent. Here is where the picture becomes genuinely unsettling. All of that data, every ISS measurement, every MRI scan, every bone density record, every case of SANS, all of it comes from people orbiting at roughly 400 kilometers above Earth's surface. That altitude is still inside Earth's magnetosphere. The ISS crew is still partially shielded. They are exposed to elevated radiation compared to the surface, but not to the full unfiltered environment of deep space. Nobody has spent multiple years in the interplanetary environment beyond the magnetic field. The combined effects of microgravity plus chronic galactic cosmic ray exposure, plus the other stresses of deep space on a human body over 2 or 3 years, are not measured. They are not approximated by ISS data. They are unknown. What that means in practice is a stack of unknowns layered on top of each other. Bone loss, muscle loss, fluid redistribution, SANs and potential brain changes, chronic radiation exposure and DNA damage, cardiovascular strain from the altered circulatory environment, likely effects on the immune system that remain poorly characterized. None of these in isolation, all of them simultaneously, for years, in an environment where no data yet exists to tell you what happens. The obvious engineering answer is to give the crew gravity, spin the ship. Centripetal force, the same principle that presses you outward when a car turns a corner, can simulate gravity if you spin a structure fast enough. In principle, it works. In practice, the details become a wall. Spin the ship too fast, and the inner ear goes wrong. The Coriolis effect, the same phenomenon that influences weather patterns on Earth, acts on fluid moving inside the inner ear when the head turns. At high rotation rates, turning your head produces dizziness, nausea, disorientation. The crew cannot function that way. To keep the rotation comfortable, the radius of the spinning structure must be large, tens of meters at minimum. Something the size of a large building or a city block, rotating continuously in space, for years. That structure must be strong enough to hold its shape under constant rotation. It must be precisely balanced, because imbalance at those rotation rates creates oscillation that compounds quickly. It needs bearings or tethers engineered to handle continuous movement across years without failure. It needs rotating joints to pass electrical power, air, and data between the spinning and non-spinning sections. It needs docking solutions that work with a rotating structure. None of these are trivial engineering problems. None are solved at the scale required, and none of it fits on a single launch vehicle. A rotating habitat large enough and slow enough to be livable is not a component you bolt onto a rocket. It is a whole category of space architecture that does not yet exist. The added mass of that structure feeds directly back into the problem described earlier. More mass means more propellant means more mass, and the cascade compounds from the surface upward. So the artificial gravity solution does not escape the problem. It redirects it. And then there is arrival. Mars has a surface gravity of roughly 0.38 g, about 3.7 meters per second squared, just over 1/3 of Earth's. A crew that has spent years in deep space, with the bone loss and muscle loss and fluid redistribution and radiation accumulation and whatever effects remain unmeasured, arrives at a planet where gravity is 1/3 of what their bodies were originally built for. They are asked to stand up, to walk, to lift equipment, to build habitats, to respond quickly if something goes wrong. They will be prone to fractures. Their joints will be under stress they are not prepared for. Falls that would be minor inconveniences for a healthy person will carry real injury risk for a body that arrived already depleted. The moon landings offer a point of comparison, but not a comforting one. Apollo crews went to the lunar surface in good physical condition. They had not been in space long enough for serious deterioration. They worked intensely in low gravity for a few days and left while still relatively fresh. That model does not extend to Mars. Beyond the moon, you are not sending a fresh crew into a challenging environment. You are sending a crew whose bodies have been systematically worn down during the journey into an environment that does not match what they evolved for and does not offer full recovery. The ship damages them on the way. The destination does not let them fully heal once they arrive. Those two facts sit at the center of what a human Mars mission actually requires of the people inside it. And the biology is only one layer of what is stacked against them. Step back from the bodies for a moment and look at the ship itself, because nearly every fix proposed for the damage that transit inflicts on a crew requires something that sounds simple and turns out to be anything but. It requires power, more power than you might expect. And the universe, as it happens, is not generous about supplying it. Start with sunlight. At Earth's distance from the sun, roughly 1,260 watts of energy arrive at every square meter of surface exposed to space. That is a bit more than a kilowatt per square meter, which is a strong signal. Solar panels convert only a fraction of it into usable electricity, but the raw input is substantial. That is why satellites and the International Space Station rely on solar arrays. The source is reliable, the fuel is free, and the panels have no moving parts to fail. At Mars, that picture starts to change. Mars sits about 1.5 times farther from the sun than Earth does on average. Because the intensity of sunlight falls with the square of distance, not linearly, Mars receives roughly 40% of what Earth gets. Not a small reduction. Less than half, per square meter, before your panels have converted a single watt. At Jupiter, you are about 5 times farther from the sun than Earth. Run the math. About 4% of Earth's sunlight. A solar array that generates 100 units of power in Earth orbit would generate 4 units at Jupiter. The same panels, the same design, a fraction of the output. For robotic probes, the engineers compensate with larger fold-out arrays. It is expensive and adds mass, but the probe has no crew demanding heat, air, water, medical equipment, and computing power around the clock. For a crewed ship, scaling up the solar panels is not a clean solution. Every extra square meter of panel is more mass to accelerate out of Earth's gravity. It is more structure, more mechanical deployment systems, more electrical connections, more surface area flying through a micrometeoroid stream at tens of kilometers per second. Bigger panels are fragile geometry, and fragile geometry in space has a way of being punished. But the power problem is only half of the thermal story. The answer is stranger than that. The other half runs in the opposite direction. Every watt of power a ship generates, from any source, eventually becomes heat. Computers generate heat. Pumps generate heat. Life support systems generate heat. The crew generates heat simply by existing. On Earth, that heat dissipates through air and water. Convection carries it away. In space, there is no air. There is no water flowing past the hull. There is only one way to dump heat, and that is by radiating it, sending infrared light outward from carefully designed surfaces until the energy leaves the ship. Radiated heat scales with surface area and the fourth power of temperature. That last part matters. You can increase the temperature of your radiators to shed heat faster, but you cannot increase it indefinitely before the materials themselves begin to fail. The fluids running through the cooling loops approach their limits, and the entire system becomes unreliable. So you cannot simply run your radiators hotter and solve the problem. You have to make them bigger, which means more panels extending into space, more mass, more structure, and more surface area exposed to micrometeoroids. The solution to the heat problem makes the fragile geometry problem worse. As a mission grows in complexity, the thermal load grows with it. More computers, more pumps, more redundant systems, more medical equipment. The heat from all of it has to go somewhere. Thermal management on a long crewed mission is not an engineering footnote. It is as fundamental as the air supply. The obvious fix at this point is to stop relying on sunlight entirely. Go nuclear. This is not a new idea. Voyager 1, Voyager 2, Cassini, Curiosity, Perseverance. All of these probes carry what are called radioisotope thermoelectric generators, or RTGs. An RTG uses the heat produced by the natural decay of a radioactive material, typically plutonium-238, and converts that heat directly into electricity through devices called thermocouples. No moving parts, reliable for decades. The source of power does not weaken with distance from the sun. The catch is the output. A typical RTG produces a few hundred watts. Think of a handful of household light bulbs. That is the power budget for some of the most sophisticated robotic spacecraft ever built. And it is enough precisely because those probes do not need to keep 6 people alive, warm, medically monitored, and physically active in a closed habitat for years on end. A serious crewed ship needs tens of kilowatts at minimum, hundreds of kilowatts for a more capable mission. You could stack more RTGs, but each one is heavy. Each contains nuclear material that demands careful handling and strict safety protocols at launch. And even a stack of them falls short of what a crewed mission requires. The real answer is a space reactor, not an RTG, a genuine nuclear fission reactor capable of delivering hundreds of kilowatts to a megawatt or more of electrical power. That kind of reactor exists in concept, and in limited experimental form. It would solve the power source problem. Wait, read that description again. A space reactor is not a battery upgrade. It is a small industrial power plant mounted on your spacecraft. It requires radiation shielding thick enough to protect the crew from the neutrons and gamma rays the reactor produces continuously during operation. That shielding is heavy. It requires cooling loops to carry heat from the reactor core to the radiators, because the reactor itself generates enormous thermal output that must be managed or the fuel rods overheat and fail. Those cooling loops are complex, pressurized systems that must run without failure for years. The control systems governing the reactor must work flawlessly in vacuum, in deep space radiation, with no maintenance crew available to replace components. Any damage to the reactor's own cooling system is simultaneously a power problem and a safety emergency. Not an upgraded battery, a miniature industrial system operating in one of the harshest environments humans have ever built anything to survive in. The mass of all this, the shielding, the cooling infrastructure, the structural support, feeds directly back into the constraint chain already covered. More mass means more delta V required to move the ship. More delta V means more propellant. More propellant means more structure. The problem compounds, as it always does in deep space. And power availability is not just a function of source strength, it is also a function of time and rhythm. Even a ship with adequate power generation faces the question of when that generation can run and when it cannot. Consider the moon. A lunar day from one sunrise to the next sunrise at the same surface location spans about 29.5 Earth days. That means roughly 2 weeks of continuous sunlight at any given point on the lunar surface followed by roughly 2 weeks of continuous darkness. For a surface base relying on solar power, every month delivers a long, cold night. Lighting, heaters, life support, communications, all of it must run through approximately 2 weeks of darkness on stored energy. Big batteries, or fuel cells, or some combination of both. Every kilowatt hour of stored overnight power is additional mass. Every additional kilogram of that mass carried to the lunar surface from Earth, multiplied through the entire launch and transit calculation. Near other planets, eclipses and orbital geometries create their own interruptions. Long passages behind a planet or moon can cut off sunlight for hours or more, all of it requiring stored power to bridge. No single eclipse is necessarily fatal, but in aggregate, the rhythms of light and shadow impose a continuous storage requirement that does not disappear just because your power source is capable. Here is the deepest part of the mismatch, and it connects directly back to everything already catalogued in this story. Every proposed fix for the problems that deep space imposes on a human crew requires more electrical power. Active radiation shielding via electromagnetic fields, if it ever becomes practical at the scale a crewed ship needs, requires enormous sustained power to maintain the fields. Better life support systems with higher recycling efficiency, more capable air scrubbers, tighter climate control, integrated medical equipment, all of them draw from the same electrical supply. Advanced electric propulsion systems, the kind that could push a ship faster over months of continuous low thrust and reduce total transit time, require a large and steady electrical supply to run their ion drives, or Hall thrusters. More protection from radiation demands more power. Faster transit to reduce radiation exposure demands more power. Keeping a crew healthy for longer demands more power. Every direction you push to make the mission safer or shorter or more survivable leads back to the same requirement. And the farther you go from the sun, the less power the universe naturally offers you, and the harder it becomes to dump the heat from whatever power you do generate. You need more power exactly when the supply is shrinking and the thermal problem is growing. That is not a coincidence. It is a structural feature of the deep space environment, not an obstacle that clever engineering might sidestep, a fundamental condition of the regime. There is one more catch, smaller in statement than in consequence. Larger solar arrays, more radiator fins, reactor shielding structures, support framing. All of it increases the ship's cross-section, the total surface area moving through space at tens of kilometers per second. More cross-section means more exposure to micrometeoroids and dust. The ship that solves its power problem by extending more geometry into space is also the ship that has given micrometeoroids more to hit. That thread will come back. That thread comes back now. The bigger you build, the more there is to hit. That is not a metaphor. It is a straightforward physical consequence of operating a large structure in an environment that is not, in fact, empty. Space looks empty. From the outside, from the pictures, it reads as a void. But the inner solar system is threaded with debris, dust grains, tiny fragments of rock and ice shed by comets, ground off asteroids, left drifting in the plane of the solar system for millions of years. They are not dramatic. Most are smaller than a grain of sand, but they are moving at tens of kilometers per second. Around 20 kilometers per second is a typical collision speed for a particle in the inner solar system. That is roughly 45,000 miles per hour. Here is where the physics stops being intuitive. A grain of sand at that speed carries roughly the kinetic energy of a rifle bullet. Not because the grain is large, not because it is dense, because kinetic energy scales with the square of velocity. And at 20 kilometers per second, even something almost too small to see is carrying an enormous punch. Every spacecraft we have ever flown comes back marked. Pits, tiny craters, peppered insulation, small chips in windows. The space shuttle's windshield had to be inspected and sometimes replaced after every mission. The International Space Station is photographed and monitored specifically for impact damage. This is considered acceptable for short missions. A few weeks, a few months, and the damage stays cosmetic. Stretch that exposure to years. The same gentle rain of particles that puts chips in a windshield over 2 weeks will chew through radiator fins, degrade solar panels, erode insulation blankets, and work at seals and joints across months and years of continuous operation. More hardware on the outside of the ship means more surface area receiving that treatment non-stop. The ship that solved its power problem by hanging more geometry into space is also the ship that gave the environment more to attack. We have a preview of what this looks like in slow motion. The Apollo astronauts encountered it on the moon. Lunar dust is not like dust on Earth. On Earth, wind and water round off sharp particles over time. The moon has neither. Its dust has been shattered by billions of years of micrometeoroid impacts, and the fragments look, under a microscope, like broken glass. Sharp, jagged, irregular. When Apollo astronauts brought it into their suits, it stuck with a static cling that was almost impossible to remove. It worked into hinges and zippers. It scratched visors. It clogged seals. When dust tracked into the lunar module settled and the astronauts removed their helmets, some reported a smell like burnt gunpowder. Visible wear on suit materials appeared after only a few days of surface operations. A few days. Stretch that to months, to years. On a planet where dust storms can spread fine particles across the entire globe, or on a low-gravity moon like Phobos where kicked-up material hangs suspended and slowly coats every surface it contacts, dust becomes more than an inconvenience. It grinds moving parts. It contaminates air filters. It shortens the life of anything that rotates, seals, or slides. What was an annoyance during a 3-day lunar visit becomes a slow, mechanical attrition campaign over a multi-year mission. Engineers designing for this problem reached for a solution called a Whipple shield. Instead of a single thick wall, you build multiple thin layers with empty space between them. A tiny particle moving at high speed shatters when it hits the first layer, and what reaches the main hull is a dispersed cloud rather than a solid projectile. The energy is spread over a larger area. The damage is reduced. But Whipple shielding is not free. It adds mass. It adds structural complexity. The supports and spacers needed to hold each layer at the right distance. And it increases the total outer surface area of the ship, which is itself now a slightly larger target for the next particle. Each protective measure changes the geometry of the problem rather than eliminating it. On a multi-year mission, the ship stops looking like a streamlined vehicle. It looks like an armored convoy wrapped in sacrificial layers, each layer absorbing punishment meant for what is inside. And when something gets through, or when something wears out, the repair calculus changes completely. The International Space Station sits about 400 kilometers above Earth's surface. When a component fails or wears beyond safe use, a cargo flight can reach it within weeks, sometimes sooner. When structural damage is discovered, a spacewalk can be scheduled. When a module is compromised, replacement hardware can be launched within months. The repair chain is intact and close. Beyond the moon, that chain is cut. A micrometeoroid strikes a coolant pipe on a deep space transit vehicle. The leak is tiny at first. By the time it shows up clearly in sensor data, the damage may already be serious. There is no spare pipe on a launch pad somewhere. There is no cargo flight that can reach the crew in any useful time frame. Whatever was packed at the moment of departure is the complete inventory for the entire mission. Nothing will be added. Nothing can be replaced from outside. A hole in a propellant tank is not a small leak. It has lost delta V. The ship arrives at its destination with less maneuver capability than planned, and every other calculation built on that capability is now wrong. A damaged radiator is not a cosmetic problem. It is reduced cooling capacity for the entire ship, and the power systems that depend on that cooling will start to behave unpredictably. And here is where the statistics come in. Think about the space shuttle, roughly 2.5 million moving parts, thousands of sensors, miles of wiring. Over the course of 135 missions, 2 orbiters were lost. Challenger in 1986, Columbia in 2003, 14 astronauts killed. That is a loss rate of approximately 1.5%. Wait, 1.5% sounds small, but run the arithmetic in the direction that matters. Fly a shuttle-class system 100 times, and at a 1.5% loss rate, you expect to lose more than 1 crew. Not as a worst case, as the statistical prediction. That was for missions lasting 1 to 2 weeks. Low Earth orbit. The repair chain intact below. Missions short enough that any individual component had to survive for only a small number of days. A multi-year mission to Mars does not offer any of those conditions. Components have to function for years, in vacuum, under continuous radiation bombardment, through thousands of thermal cycles between brutal cold and direct sun exposure, with no maintenance, no overhaul, no replacement. The concept used to describe component longevity is mean time between failures. It describes how long a part typically runs before it fails. On Earth, mean time between failures matters mainly as a guide for maintenance schedules. A part fails, you replace it, you move on. In deep space, there is no replacement. So the mean time between failures for every critical component has to exceed the entire mission duration, under conditions far harsher than the component was likely ever tested against. Aircraft carrier levels of reliability built into something more like a submarine that can never surface, never dock, and never return to port for the entire duration of the mission. Spares are the obvious answer. Pack extra pumps, extra valves, extra sensors, extra boards, but every spare adds mass. Mass triggers the propellant cascade, and the propellant cascade reaches back to the rocket equation, which compounds exponentially. There is no free spare. Every extra component you bring to protect against failure is also additional launch mass, additional transit mass, and additional delta V demand from departure all the way to arrival. But even that framing understates the real problem. A complex vehicle is not just a collection of independent parts. Every system talks to every other system. A sensor drift in one place feeds signals into control software that manages something else entirely. In January 2010, a minor fault in a power distribution system aboard the International Space Station triggered a cascade that briefly disabled one of the station's coolant loops. No single component had failed catastrophically. The cascade came from interactions. On a long mission with aging hardware and continuous radiation and impact stress, small faults accumulate. A radiation-induced drift in a temperature sensor reports a slightly wrong value. The control software reads that value and interprets it as an overheating loop. It ramps up a pump to compensate. The extra load stresses a power converter. The converter overheats and shuts down. A module loses power. Real temperatures start to climb. Alarms begin to cascade across systems that share that module's power bus. Nothing was broken at the start. The fault propagated through interconnections until something genuinely critical was at risk. The more functions you cram into a vehicle, the more interconnected everything becomes, and the more paths exist for small problems to grow into large ones. Over a mission measured in years, with no maintenance, with aging components, with a structure that has been absorbing impacts and radiation for months, the probability of at least one such cascade does not stay small. It approaches certainty. This is what engineers sometimes call the impossibility curve. Plot mission duration against the probability of losing the crew. Short missions tolerate cruder hardware. Rare failures rarely show on short timescales. Apollo sat in a forgiving zone. ISS missions sit in a more demanding zone but stay manageable because the repair chain is always close. As duration stretches from months into years, the reliability requirements climb faster than any plausible hardware improvement. The curve bends sharply. Multi-year crewed missions beyond the moon sit on the steep part of that curve, in a region where the requirements exceed what we know how to build, and where the consequences of falling short are total. That is not the end of the accounting. There is one more layer to what makes deep space so unforgiving, and it has nothing to do with hardware or propellant or bone density. It has to do with something simpler, something we have taken for granted since the first human left the ground: the ability to ask for help. Think about how spaceflight has always worked. A crew in orbit or on the surface, a room full of engineers on the ground, both groups watching the same telemetry, sharing the same problem, talking back and forth. That relationship was not incidental to Apollo. It was structural. The onboard computers were modest by any modern standard. The crew was highly trained, but small. What made Apollo possible was that a team of hundreds could reach into the mission in near real time and think alongside the crew when something went wrong. That was possible because the moon is only 1.3 seconds away at the speed of light. Round trip, the delay is roughly 2.5 seconds. Uncomfortable, like a bad international phone call, but workable. You could ask a question and hear an answer before the situation changed. Engineers could watch a burn unfold and intervene. The cord was stretched thin, but it held. The moon was the last place in the solar system where that cord holds. Mars cuts it. At best, when Earth and Mars are close in their orbits, a one-way signal takes about 4 minutes to arrive. At worst, when the planets are on opposite sides of the sun, that delay stretches to roughly 24 minutes one way. Round trip, you are waiting anywhere from 8 minutes to 48 minutes between sending a message and receiving a reply. Not a delay, a different world. You cannot joystick anything across that gap. No ground controller can fly a lander down through the Martian atmosphere in real time. The physics will not allow it. This is why every Mars landing has been described as 7 minutes of terror. The lander hits the atmosphere, the parachutes deploy, the descent sequence runs, and the vehicle touches down all in a few minutes. But the signal showing what happened takes another 24 minutes to reach Earth after the fact. Mission Control does not watch a landing. Mission Control waits for a binary result, success or silence. For robotic rovers, this is workable. Send a batch of commands in the morning. The rover executes. Hours later you see what happened. Diagnose, plan the next batch. Slow, but manageable. A robot can wait. A robot has no crisis that requires an answer in seconds. A human crew is different. A human crew can have a crisis right now. A pressure drop in the habitat. A cooling loop failure. A medical emergency. These events do not wait 48 minutes for a round-trip reply. And this is only Mars, the closest destination anyone seriously considers. Move further out and the numbers become staggering. Jupiter sits so far from Earth that a one-way signal takes roughly 30 to 50 minutes to arrive. Round trip, up to about 2 hours. Saturn, Uranus, Neptune, hours one way. The Kuiper Belt, where Pluto drifts and other small bodies accumulate, turns radio communication into something closer to slow mail. You send a message today and receive an answer tomorrow. For a crew at those distances, calling home for help becomes sentimental, not operational. By the time a distress message arrives at Earth, is read, is understood, is discussed among engineers, and a reply is formulated and transmitted. The situation on the ship has already resolved, one way or another. Earth does not become mission control. Earth becomes background support, a quiet voice in the archive. Then the pattern breaks. The solution to losing ground control is to build the control into the ship itself. The vessel must become largely self-managing. It must detect faults before they cascade. It must isolate failing hardware before the failure spreads. It must reconfigure around damage. It must guide the crew through emergency responses without waiting for Earth. Automated navigation, local power routing, self-monitoring life support, diagnostic systems that function even when the communication link is down. The ship effectively becomes a small independent space station with its own brain, capable of making critical decisions without a human engineer anywhere near the loop. That solves one problem. It creates another. Every layer of autonomy is more software, more code paths, more sensors feeding data into systems that make decisions, more actuators responding to those decisions, more interactions between all of them, and more places for something to go wrong in a way the designers did not anticipate. You trade one impossibility for another. Real-time human control from Earth was the first impossibility. Flawless complex automation running for years in an unforgiving environment becomes the second. You do not escape the problem. You translate it. There is also a human cost that sits beneath all of this. Quieter, but just as real. On the International Space Station, crews make near real-time video calls with family and with ground controllers. Voices overlap. Faces are visible. The feedback is immediate. Earth feels close, not because the astronauts can touch it, but because the conversation feels like a conversation. That matters more than it sounds. We are not wired for silence. We are wired for sub-second responses. A raised eyebrow, a shift in tone, the slight pause before someone answers. These are the signals we use to read the world around us, to calibrate our own state, to feel that we are not alone. Stretch those signals to tens of minutes, and something breaks. A crew member sends a message to a spouse. The answer arrives 40 minutes later, a reply to words already half forgotten. A crew member reports a problem to mission control. The reply comes back suggesting a procedure that was tried 30 minutes ago. Every conversation becomes a delayed monologue. You speak into the void, and eventually the void responds, and by then, you have already moved on to whatever came next. A small crew, in a small metal volume, months or years from home, with half-hour ping times, is not merely technically isolated. The isolation is psychological. The cord that held during Apollo, that stretched but held, does not just fray at interplanetary distances. It goes quiet entirely. The ship carries everything it needs, but it also carries everyone it has, and those people are alone in a way no training simulation can fully prepare for. And the autonomy the mission depends on, the software brain managing faults and routing power and guiding repairs, has never been proven over years. In the deep radiation environment, under the accumulated stress of a long mission, making life or death decisions without a human engineer in the room, whether that autonomy can be made reliable enough is one of the open questions that sits at the center of every serious deep space proposal. It is not a detail. It is the question the rest of the architecture depends on. The cord is cut. The ship must be its own ground control. Whether any ship we can build is ready for that is something we do not yet know. One of those systems is running right now. It was running during every moment of communication delay covered in the last section. It will run without pause for the entire duration of the mission. Not the navigation system, not the propulsion system, the one that gives the crew air to breathe and water to drink. The one that, if it stops working, ends the mission in days. The question is deceptively simple. How do you keep people breathing, eating, and drinking for years when no one can bring more supplies? The first answer humans ever used was the obvious one. Bring everything. Apollo did exactly that. Oxygen in pressurized tanks, water in storage, food in packets, and chemical canisters filled with lithium hydroxide, a compound that absorbs carbon dioxide from the cabin air. When a canister fills up, you swap it out. Simple, reliable, entirely disposable. For a mission lasting a few days, this works. The total mass of consumables stays manageable. A few tons of supplies for a short crew on a short trip. Apollo was designed around that logic, and the logic held. But here is where the math turns on itself. Each person needs several kilograms of water, oxygen, and food per day. Add packaging, CO2 scrubbers, and basic hygiene. Multiply that by a crew of 4. Now stretch the mission to 3 years. The number you get is not uncomfortable. It is not slightly large. It is tens to hundreds of tons of consumables. And that is before redundancy, before waste management, before accounting for every pump and filter and sensor that also has to make the trip. You run out of launchpad space before you run out of mission days. Open loop life support simply does not close the math at that scale. The obvious refinement is recycling. The ISS already does this, roughly 400 kilometers above Earth. The station recovers a significant fraction of its water from 2 sources, the moisture in the cabin air and the crew's urine. Both get processed through filtration and purification systems and returned as drinkable water. Carbon dioxide scrubbers regenerate rather than just fill up and get discarded. The system reduces how much has to be shipped up from Earth. Not to zero, but enough to keep the station viable between cargo flights. Here is what that system depends on. Cargo flights. Regular ones. Food still arrives from Earth on a predictable schedule. When a pump wears out, a replacement is launched within weeks. When a filter bed degrades faster than expected, an emergency resupply is possible. The ISS recycling model works because the warehouse is 400 kilometers below the station. You can reach it in hours. Now imagine the same support system with the warehouse 200 million kilometers away. A water recovery component fails. There is no replacement. A CO2 scrubber bed exhausts early. There is no emergency launch. The ISS model does not degrade gracefully at that distance. It becomes a trap. Every part that keeps the crew alive has to last the entire mission, because nothing from outside is coming. This pushes toward a more ambitious idea: bioregenerative life support. Instead of machines that process waste, you use life. Plants, algae, and microbes grow food, recycle biological waste, and release oxygen as a byproduct. A small closed ecosystem, a tiny farm and a chemical plant wrapped together in a pressurized canister. In theory, the loops close completely. Waste becomes nutrients. Nutrients become food. Food becomes waste again. In practice, a living system is a delicate system. Plants need stable light, controlled temperature, the right balance of nutrients in the water, and carefully managed humidity. A small fluctuation in any of those can reduce yield. A larger disruption can collapse a crop entirely. Microbial bioreactors, the tanks of bacteria and algae used to process waste, need their own precise conditions. Too warm and the community shifts. A contaminant reaches the tank and the biology crashes or overgrows in the wrong direction. A pathogen reaches the food crops. On Earth, you call a supplier. You import food. You switch farms. In deep space, that failure chain leads somewhere specific. Rationing, then starvation. Partial closed-loop systems have been tested on Earth and in small space experiments, but nobody has ever run a fully closed, fully reliable, fully human-occupied bioregenerative system for years under real microgravity and real radiation. Not in orbit, not on the ground, not anywhere. Betting a multi-year deep space mission on a biological system never proven at that scale, in those conditions, with no fallback, is not a calculated risk. It is a different category of problem entirely, and the air itself adds another layer. A pressurized habitat holds roughly 1 atmosphere of pressure, about 101 kilopascals, about 14.7 pounds per square inch. That pressure pushes outward against the hull at every point, constantly. Seals age, joints flex as temperatures swing between direct sunlight and shadow. Micrometeoroids, the same particles covered earlier, create pinholes. A tiny leak that you would not notice over a week becomes a measurable problem over a year. Over several years, it becomes serious. The threat from inside is quieter, but equally persistent. Plastics off-gas trace chemicals into the cabin air. Equipment leaks vapors. Contaminants accumulate slowly in concentrations too low to detect without sensitive instruments. Filters, catalytic converters, sensors and control software all work continuously to keep the atmosphere safe. A filter that quietly degrades past its effective range. A sensor that begins to misread and reports clean air when the air is not clean. These are not dramatic failures. They are slow-motion emergencies that may not announce themselves until they are already serious. Every system added to address these problems carries its own cost. Water recycling requires pumps, membranes, filters, heaters, tanks, and the electronics to control them. CO2 scrubber regeneration adds hardware and software on top of that. Growing food adds lighting arrays, nutrient delivery systems, climate control loops, and biological monitoring equipment. Each closed loop reduces dependency on resupply and adds new things that can fail. More valves that can stick, more pipes that can clog, more sensors that can drift, more software running, more decisions with no engineer available to review them. Life support stops being a machine that provides air and water. It becomes a ship-wide industrial plant that must run continuously, without a major failure, for years. And the crew's role shifts with it. The time spent on science, on observation, on the work the mission was designed for, competes with the time required to maintain the floating factory keeping everyone alive. Whether a fully closed, fully reliable, fully maintainable life support system for a multi-year beyond the moon mission is something we are close to building, or a story we tell ourselves to avoid saying we are not ready yet, is a genuinely open question. Not a pessimistic framing, an honest one, and life support is only one of the systems the crew is responsible for maintaining. It is not the last one, and life support is not even the largest barrier waiting on the other side of that question. Pull back from the hardware for a moment. Imagine every engineering problem in the previous chapters was solved. The radiation shielding worked. The life support cycled without failure. The crew arrived physically intact. The autonomous systems handled everything ground control could not. Every technical box checked. And then someone has to actually pay for it. The Apollo program cost roughly $25 billion in 1960s money. In today's terms, that figure lands somewhere between $150 and $200 billion. Think about what that bought. A few test flights, some Earth orbits, 6 successful moon landings, each a 1-week round trip to a destination only 3 light seconds away. No permanent base, no reusable transport system, no production line of affordable follow-on missions. Apollo was a single, enormous effort, built at war-scale urgency during a unique Cold War moment, and it was shut down the moment the political motivation faded. 3 planned landings were cancelled outright, not because the hardware had failed, but because the will had. That was the moon. Mars is not the moon. A serious, sustained crewed campaign to Mars requires cargo pre-deployment missions years in advance. Crew vehicles, return vehicles, surface habitats designed for years of occupation, redundant systems for every critical function, then more cargo flights, then backup vehicles, then replacement parts, then another crew rotation. The realistic cost of a long-term Mars program, honestly accounted across decades, is not one Apollo. It is many Apollos stacked on top of each other, one after another, with no pause and no finish line visible for a generation. The numbers settle somewhere in the multi-trillion-dollar range. And beyond Mars, it gets worse. The question is no longer whether rockets can work in principle. The question is whether any economic system will ever actually commit that much, for that long, with no quick payback and guaranteed overruns. Look at the launch cadence the world operates at today. Hundreds of launches per year worldwide, most of them small to medium payloads, satellites and resupply and commercial cargo. Heavy lift rockets, capable of tens of tons to orbit, fly only a handful of times per year each. Now consider what a real deep space architecture demands. Assembling a large crew vessel in orbit, filling a propellant depot, sending cargo ahead of the crew, then launching the crew itself, could require dozens to hundreds of large launches for a single fully built and fueled mission. That is at the shielding and redundancy levels this kind of mission actually requires. Think about what that means. You would need to build a fleet of enormous vehicles, use each one once, and repeat the entire manufacturing and launch process for every mission. The industry supporting that does not exist today. It would have to be built from scratch. Factories, launch complexes, supply chains, fuel production, all pointed at one goal, sustained across decades. And the infrastructure they would need to use does not exist either. Orbital fuel depots capable of storing cryogenic propellants for months or years without them boiling off. In-space construction yards, assembling large structures from components rather than launching them as a single piece. Lunar or orbital manufacturing turning local materials into propellant or shielding or structural components. Right now, there is one aging research station in low Earth orbit, a few small demonstration missions testing early refueling concepts, and no persistent industrial presence in space of any kind. Announcing a sustained crewed campaign to Mars from this starting point is something like announcing weekly transoceanic crossings in an era when every ship is still being built by hand from wood. But the data shifts here. Even if the infrastructure could be built, there is the question of what gets left undone while building it. $10 billion committed to a single deep space mission is $10 billion not spent on communication satellites, Earth observation platforms, climate monitoring networks, navigation infrastructure, or smaller robotic science probes that cost a fraction as much, carry essentially no risk to human life, and return clear and immediate benefits. Crewed missions beyond the moon are high risk, fragile to political shock, and nearly guaranteed to run over budget. If a crew is lost, public and political support can evaporate overnight. If everything goes right, the clear economic return remains close to zero. The result is a consistent funding pattern across every spacefaring nation. Money flows steadily to low Earth orbit and to robots, and only in rare bursts to high-risk, crewed exploration. That pattern is not a failure of vision. It is a rational response to the actual trade-offs. Physics on the whiteboard says a Mars mission is possible. Economics in the real world quietly says we are not building that at the required scale. This is what impossible means in this context. Not that no rocket could ever be constructed, not that the laws of physics forbid it, but that if a civilization will not actually commit multi-trillion-dollar sums across decades on a project with high fatality risk and no guaranteed return, then functionally the outcome is the same as if it were physically forbidden. The barrier is social and economic. It blocks just as effectively as gravity or radiation. It just does not look like a wall. Now consider the one barrier that is not about money at all. Every robotic spacecraft sent toward a potentially habitable world goes through planetary protection procedures. Clean rooms, heat sterilization, chemical treatment. The goal is to reduce the number of surviving Earth microbes on the spacecraft to the lowest achievable level. Scientists want to know if life is ever found somewhere, whether it was there before we arrived. So they minimize what we bring with us. For a robotic probe, this works. For a human crew, it is impossible. You are a walking ecosystem. Trillions of microorganisms live on your skin, in your gut, in your lungs. You shed skin cells continuously. You exhale moisture. You leave biological traces on every surface you touch. You cannot be sterilized. You cannot be clean to planetary protection standards. The moment a human steps onto Mars, Earth biology goes with them. This creates two consequences that cannot be engineered around. The first is scientific. If humans land on Mars and microbial life is later detected in the soil or subsurface, proving that life is not Earth contamination that followed the crew becomes extremely difficult. You risk permanently clouding the answer to the most profound question in science. Are we alone? The second consequence is environmental. If Mars hosts its own native life, or if the subsurface oceans of Europa or Enceladus do, introducing Earth organisms could crowd out what is already there, alter the chemistry, trigger interactions no one can predict. We might wipe out an alien ecosystem before we fully detected it, and the problem runs in both directions. Bring samples back from Mars or from a subsurface ocean anywhere in the outer solar system, and you have to ask whether something in that material interacts badly with Earth biology. Most experts believe the probability of a genuinely dangerous alien pathogen is low. Life that evolved independently on a different world may simply not be equipped to infect Earth organisms. But low probability multiplied by catastrophic consequences is still a calculation that demands serious attention. Serious sample return plans already require high containment facilities, multiple quarantine layers, strict handling protocols, and international agreements about who decides what is safe to release. Those agreements do not exist yet in the form a crewed mission would require. Set alongside the biological questions are the legal ones. The Outer Space Treaty was written in the 1960s. It established principles: no sovereignty over celestial bodies, nations responsible for their space activities. It was not written for multi-decade human colonies. It was not written for commercial mining operations on the Moon or Mars. It was not written for private companies funding their own interplanetary missions. Long-term crewed bases raise questions the treaty simply does not answer. Who owns water ice extracted from the lunar South Pole? If a company funds a Mars base, what rights do they hold over what they find? If a mission contaminates another world, who is liable? And inside the ship itself, months from Earth, whose laws govern a conflict between crew members from different nations? Jurisdiction in deep space is improvised at the exact moment when stability matters most. Then there is the question that sits underneath all the others. At what point does it become ethically indefensible to launch a crew when the chance of dying is large and the chance of meaningfully helping is close to zero? We accept dangerous expeditions on Earth, Everest, deep ocean dives, Antarctic winter overs, partly because rescue remains possible, and partly because decades of accumulated experience have refined the risk to something quantifiable. Deep space multiplies the risk and removes the exit entirely. They volunteered closes part of the conversation. It does not close all of it. Society still has to decide what level of risk it is willing to impose on human beings, even willing ones, and for what purpose. That conversation has not happened at a global scale. It has barely begun. None of these constraints add kilograms to the manifest. None of them show up in a delta V calculation. But they slow everything down with negotiations, safety reviews, regulatory frameworks, ethical debates, redesigns, and delays. Each one is a filter. Combined, they form something that looks less like a set of problems waiting to be solved, and more like a civilization that is not yet ready to make this choice. And the engineering barriers are only the beginning of that story. The filters are real, the delays are real, but all of that looks outward, at the civilization that must decide, at the money and the law and the ethics. Now go back inside the ship, back to the person sitting in that metal tube, weeks out from Earth, months still to go. Ask what it costs to be that person. Not in delta V, not in dollars. In the currency the body uses, in the currency the mind uses. On the International Space Station, astronauts already report something that surprises people who haven't thought about it. Stress. A strange feeling of separation. A quiet disorientation that sets in even at 400 kilometers up. And yet the ISS is close. Close enough that Earth fills a significant portion of the window. You can see continents shift beneath you. You can watch weather systems spiral across the ocean. At night, city lights trace the coasts of countries you know by name. If a serious emergency happens, a return capsule can have the crew home in hours. Mission control is a fraction of a second away. Family calls are nearly real time. The cord between astronaut and Earth is stretched, but it holds. It is taut and warm and present. Past the moon, that chord goes quiet. Earth stops being a globe with weather and coastlines. It becomes a bright point of light, one among many, behind you and receding. There is no down there in any intuitive sense. There is only back there, far behind your trajectory, getting smaller. The planet where everyone you know lives is no longer a place you can see. It is a direction. And that shift from globe to dot is not merely aesthetic. It is something the human nervous system registers in a way we don't fully understand. Human brains evolved in small groups on the ground. Familiar cues everywhere. Landscape, weather, horizon, the faces of people you'd known for years. Not in sealed metal cylinders drifting through black space with no immediate way back. We have some comparison points. Submarine crews spend weeks underwater in tight quarters. Polar research stations in Antarctica confine small teams through months of winter isolation. Remote mining and drilling camps cut people off from ordinary life for extended stretches. All of them report the same pattern. Tension builds, arguments over small things, the grinding strain of the same faces every day, boredom that sharpens into something harder to name, but something was wrong. Every one of those environments has a psychological safety valve that a deep space ship does not. A submarine can surface, a polar crew can be evacuated if conditions become dangerous. A mining camp can rotate workers out. If a personality conflict deteriorates badly enough, relief is days or weeks away. The valve exists, even if nobody uses it. On a ship beyond the moon, there is no valve. Every argument happens inside a sealed system nobody can leave. Every personality clash, every bad day, every slow erosion of trust between two people who have to work side by side on critical tasks, all of it stays inside. There is no spare human to slot in if someone mentally checks out. The ship is the world. The world is only as stable as that small group's ability to stay functional under continuous pressure for months and years. And then there is what happens to the body's clock. The human body expects a 24-hour cycle, not as a preference, as a biological requirement. Hormones, core temperature, alertness, immune function, all of them follow a rhythm set by sunrise and sunset. On the ISS, even with a sunrise every 90 minutes because of the orbital period, the crew maintains that rhythm artificially. Carefully designed lighting schedules, structured routines, blackout periods for sleep. Without that engineering, sleep quality collapses quickly. In deep space on a multi-year mission, there is no natural day-night cycle, just artificial lights and screens and the demands of mission operations. Alarms go off when the schedule says they go off, not when the body's ready. Maintenance, experiments, emergencies, shift work at hours that drift further from anything the body recognizes. Crew members begin to cycle out of phase with each other. One person sleeping while another is at peak alertness. Rhythms fragmenting. Sleep deprivation is not a background inconvenience. It erodes judgment. It slows reaction time. It flattens mood and sharpens conflict. Stack that on top of isolation, high workload, and a continuous low-level awareness that any serious failure is the end, and you are pushing human performance toward its outer limit. Not for a sprint, for years. That awareness is its own weight. On the moon, the feeling that rescue might be possible never fully disappears. Apollo 13 made that real. A crew that survived an explosion 56 hours out because the moon was close enough to use a free return trajectory, because orbital mechanics allowed a path home, because 4 days was survivable. That mission lived precisely because the distance permitted survival. Beyond the moon, on a Mars-class trajectory or farther, that feeling disappears. Not slowly, all at once. Everyone on board knows that if something serious goes wrong, there is no backup ship, no rescue launch, no rapid return. The true survival odds are unknown, probably worse than anything we would accept in aviation. Possibly worse than anything we would accept in extreme sports. Training people to sit with that knowledge and still respond calmly when alarms sound at 3 a.m. ship time is not a solved problem. You are not simply selecting the bravest. Bravery is not the right word. You need people whose minds will not fracture under continuous low-level awareness that any major failure is the end. That is a different thing, a harder thing, and we do not fully know how to find them, or whether the years of confinement will reveal something selection never caught. This is the part of deep space mission planning that gets called soft. Rocket thrust has numbers. Shielding mass has numbers. Psychology gets treated as something addressable with motivation, careful selection, and maybe a counseling protocol. But in a deep space mission, the human psyche is as mission critical as any pump or engine. Think about what that actually means. A fire breaks out in a crew module, or an ammonia leak in the cooling system. In that moment, if one crew member panics and freezes, or runs the wrong direction, or blocks a hatch at exactly the wrong second, the result is the same as a blown pressure valve. Everyone dies, not from equipment failure, from one person's nervous system making the wrong call under unbearable stress. If a key crew member slips into deep depression halfway through the mission and stops maintaining systems properly, the safety margins do not collapse all at once. They collapse quietly. Inspections missed. Small errors unreported. Decisions slightly worse each week. A ship drifting toward catastrophe on a curve so gentle, nobody notices until the margins are gone. If trust breaks down between crew members, people start hiding small errors, misreporting system data, the kinds of cascades that become more likely not because of equipment failure, but because the humans running the equipment stopped being honest with each other. You cannot bolt redundancy onto people. You can train, screen, monitor, but there is no spare pilot to slot in, no spare medic, no spare commander. There is no hospital to evacuate to. There is no rotation schedule. The crew that left is the crew that finishes, or the crew that doesn't. Every deep space mission with a human crew is not only an engineering test, it is an emotional brinkmanship test, pushing a few minds into a situation no human being has actually lived through for years, with no exit and no certainty of return. We are betting that the same species that starts fights on airplanes and argues in traffic jams can hold itself together in a metal tube with no exit, no real-time help, and no guarantee of coming back. That bet might be right, but it has never been tested. And what happens when it turns out to be wrong at a critical moment, 300 million kilometers from anyone who could help, is not a soft question. It is the same kind of question as a blown valve. It is just harder to put in a specification document. The body, the clock, the trust, the weight of knowing. None of those appear in the mass budget, but they are there. And the answers to whether any of it holds over the full duration of a mission are waiting somewhere ahead of us, untested, in the silence past the moon. Pull back one more time, past the bodies, past the ships, past the societies that build them, all the way out to the rules that govern everything, the physics that the universe actually runs on, and ask what those rules say about all of this. The answer is the same, but it is written in harder language. The speed of light is roughly 300,000 kilometers per second, about 186,000 miles per second. That number is not just fast, it is a ceiling. Anything with mass cannot reach it, cannot exceed it. That much we know with as much confidence as we know anything in physics. Science fiction offers hyperspace, warp drives, folds in space, tunnels through dimensions. Real physics, as far as we know today, offers none of those. What it offers instead is the velocity squared penalty, and that penalty is unforgiving. Here is what that means in practice. The kinetic energy an object carries depends on the square of its speed. Double your speed, you need 4 times the energy. Triple it, 9 times. Push to 10 times your original speed, you need 100 times the energy. The curve does not climb steadily, it explodes. A 1-ton spacecraft, roughly 1,000 kilograms, traveling at just 10% of light speed, would carry energy in the range of large nuclear arsenals, not pointed outward, not detonating, just packed into the motion of one object. And that energy must eventually be shed. You cannot coast past your destination. You must brake. The deceleration costs as much as the acceleration. You have 2 energy bills, not 1. The reading comes back reversed. Even 10% of light speed is so far beyond anything we can currently build that it barely belongs in the same conversation as real engineering. Inside our own solar system, pushing a crewed vehicle to even a few percent of light speed would require power systems many orders of magnitude beyond anything we have ever made. We are not close. We are not approaching close. So the obvious question follows. What about the exotic drives? The technologies we are actually working on? 3 of them get mentioned most often. Fusion propulsion would use the same reaction that powers the sun, releasing enormous energy from small amounts of fuel. The energy density is real. The problem is also real. After decades of sustained research and billions of dollars of investment, we have no commercial fusion power plant on Earth, only experimental reactors. And that is before you shrink one, harden it against years in a radiation and vibration environment, and make it flight-ready on a moving crewed vehicle. Fusion propulsion may arrive someday, but it is not an engine. Not today, not close to today. Antimatter drives go further. When matter meets antimatter, nearly all of the mass converts directly to energy. The efficiency is extraordinary. The production is not. We can make antimatter in particle accelerators in nanogram quantities, billionths of a gram, at enormous energy cost. Storing it is its own catastrophe waiting to happen, because any contact with normal matter annihilates both instantly. To fuel serious interstellar propulsion, you would need kilograms of the substance. Producing and storing kilograms of antimatter is not an engineering challenge we are close to solving. It is, in a plain sense, a different civilization's technology. Beamed sails, like the breakthrough starshot concept, use powerful lasers or microwave emitters to push a thin reflective sail through space without carrying fuel at all. The most serious proposals on the table would push probes lighter than a small coin, gram-scale objects, to a fraction of light speed. Not habitats, not crew. When you start scaling a beamed sail to carry human beings with life support, food, water, radiation shielding, and the rest of the stack, you return immediately to the same mass problem. The required laser power becomes planetary in scale. The infrastructure needed to build and aim it does not exist. Not sketches of working engines. Sketches of ideas for working engines. That is where we are. Now hold that alongside the actual distance. Alpha Centauri, the nearest star system to our own, sits roughly 4.37 light-years away. In kilometers, that is approximately 41 trillion. Voyager 1, one of the fastest objects ever built by human hands, moves at about 17 kilometers per second. At that pace, reaching Alpha Centauri would take on the order of 70,000 years, longer than recorded human civilization. To compress that journey into a single human lifetime, you would need speeds that make the energy and engineering problems described above look mild by comparison. And a human lifetime is not long, roughly 80 years if everything goes well. Against the distances of the solar system alone, that span is barely a rounding error. A crewed mission to the outer planets at realistic speeds runs easily into decades round trip, and that is before radiation, mechanical failure, life support, and the rest of the stack begin compounding. To make crewed interstellar travel something other than a thought experiment, you need generational ships, where crew members live and die on board, and only their descendants arrive. Or you need reliable suspended animation, biologically pausing people for decades at a time. Or you need lifespans extended so radically that a century in transit is just one chapter of a much longer life. We have none of those. None of them are close to existing. Now, pull back further and look at all of it at once. Radiation, bone loss and muscle atrophy, life support that must never fail, power systems that do not yet exist, debris and micrometeoroids grinding the hull over years, communication delays that cut the crew loose from Earth in real time, psychological isolation with no exit, economic cost measured in trillions across decades, planetary protection and legal frameworks not yet written, an energy ceiling imposed by physics itself. Each one of those, taken alone, looks hard but not impossible. Each one has a partial solution. The partial solutions have costs. The costs feed back into the other problems. And here is the thing that changes the character of the whole problem. You do not solve these one at a time. You solve them all simultaneously, on the same vehicle, for the same mission, while the solutions interact. Add shielding and the ship gets heavier. A heavier ship needs more propulsion. More propulsion means bigger tanks. Bigger tanks mean more structure. More structure means slower acceleration. Slower acceleration means a longer trip. A longer trip means more cumulative radiation, more time for hardware to age, more time for the crew to deteriorate. Close the life support loops and you are running a small chemical plant and a small farm on board, adding complexity and cascade failure risk. Add redundancy and you add hardware, mass, power, heat. Push toward autonomy and you add software, sensors, new bug surfaces, new failure modes. Make the crews psychologically bearable and you add volume, private space, amenities, all of which cost mass and power. Every fix feeds another problem. It is like climbing a slope made of loose gravel, where every step forward makes it easier to slide backwards somewhere else. Some people hear all of this and say, give it time. Technology always advances. We will get there eventually. But look at the empirical record. Humans last walked on the moon in 1972, more than half a century ago. Since then, crewed spaceflight has not slowly marched outward. It has stayed in low Earth orbit. Skylab, Mir, the International Space Station, shuttle flights circling a few hundred kilometers above the surface. Robotic probes have gone everywhere. Mars, Jupiter, Saturn, Uranus, Neptune, past Pluto, into interstellar space. Crews have not moved. The envelope of where we actually send human beings has not expanded since Apollo. That is not a curve bending toward the stars. That is a plateau, and a plateau is itself evidence. It tells you something about the gap between what is technically conceivable and what civilizations like ours actually do. Becoming a deep space species would require not just time, but simultaneous revolutions in propulsion, medicine, materials, artificial intelligence, industrial capacity, and international coordination. None of those revolutions are guaranteed. None of them are on a near-horizon schedule. This is what impossible actually means in this context. Not that no universe could ever permit this. The physics does not forbid these missions. It allows trajectories, calculates energy budgets, and shows the paths. But it also shows the costs clearly, and the costs do not bend to wishful thinking. The impossible here is operational and civilizational. No society like ours is actually going to do this in any time frame that matters to a person alive today. We have shown the capacity for efforts of that scale exactly when survival, war, or immediate profit demanded it. Crewed missions beyond the moon offer none of those. So the money flows to low Earth orbit, to robots, to satellites that pay for themselves, and the frontier stays where it has been since 1972. Humanity is not a deep space species. Not yet, and not in any trajectory we can point to and call honest. It is a coastal species, hugging the shore of one planet, circling in low orbit, visiting the moon once in a distant decade if ambition and politics align for a moment. The Earth-Moon region is a shallow tidal pool, and right now, that is as far as we can realistically swim. Beyond the moon sits in the same category as faster-than-light travel. Not something the universe strictly forbids, but not something that will be a normal part of human life. Not something the physics of our bodies, our ships, our energy systems, our economies, or our psychology currently supports. The silence past the moon is not an invitation. It is a fact, and all the constraints stacked in this story are the reason why.